Hello everyone, welcome to what will be our pre-lecture for class number 3 this semester. Just a reminder, let me do my best YouTuber impression here. If you want to know exactly when these videos post, like and subscribe for more. Okay, alright, getting into what you should know by the end of this class. Essentially, you should know more about significant figures, scientific notations, and metric units and prefixes. We're also going to cover some atomic models in this video and then in class. Okay? So, significant figures are a way that we convey a measurement's magnitude and uncertainty. That is to say, how big our number is and how precise it can be. Okay? So the number of significant figures in a number is the number of digits that are known exactly plus one whose value is uncertain when we make the measurement itself. For determining the number of significant figures in a number, I'm going to go through the rules here. So all non-zero digits and any zeros between other digits are considered significant. So in this first example here, we have 1.0089. That would be 5 sig figs. Something I should say is I often abbreviate significant figures as sig figs, so as you hear me say that, that is what that means. Our second rule is that any leading zeros that we have are never significant. So if we have a decimal here, for example, 0.025 and then 0.00000025, each of those would only have 2 significant figures. Okay? Next rule is that any trailing zeros without numbers containing a decimal point are not significant. So in this example, 3400 only has 2 sig figs. Then finally, any trailing zeros in a number with decimal points are always significant. So even if it's a decimal here, if our decimal comes before our non-zero digits, this would have 3, 450. If we finish it with a decimal point, would have 3 significant figures, and 45.0. All of those have 3 sig figs. Okay? For calculations, we're not going to be doing any calculations this week, but we'll be getting into them before too long. So I'm going to go through the rules here as a preview, and then we'll cover them more thoroughly later. So for multiplication and division, when you're doing math with these numbers, your answer should contain the fewest number of sig figs for any number used in that calculation. Okay? When we're doing addition and subtraction, the calculated answer must contain the fewest number of places after the decimal point of any number used in the calculation. And so that can be a tricky one that often gets people. And again, we'll review this by the time we get to doing some more calculations in class. Number 3, any numbers that are exact. So think conversion factors. If you want to think about like a dozen being 12, that has an infinite number of significant figures, and it will not limit the number of sig figs in any calculation. That's ultimately because conversion factors are exact. Okay? So they're exact things, they're not measurements that we're making. Okay? Another part of chemistry with regards to numbers that's going to be important for you to understand this semester is scientific notation. So when numbers are very large or very small, oftentimes it's easiest to express them using scientific notation. What that means is that we have a single digit on the left side, so something between 1 and 9 usually, on the left side of the decimal, with the remaining number of significant figures on the right side of the decimal, followed by times 10 to some number. So I represent that with a lowercase n right there. That lowercase n is just going to be some number. Okay? If n is a positive number, that means that the number in scientific notation is large and that the decimal would move to the right. If n is negative, it does not mean our number is negative, it just means that the number is very small and our decimal would move to the left. So some examples here, say 1.882 times 10 to the 6th, that is the same thing as 100 or 1,882,000. Okay? 7.4 times 10 to the negative fourth. Again, our number is not negative, it's just small. So it would be 0.00074. And one way I kind of keep track of how to move decimals is if this is to the negative fourth, we could just say 1, 2, 3, 4 places over, and we get our 7.4 again. Okay? This very large number here is called Avogadro's number. We're going to talk about it some more in the coming weeks, but it's a very common one in chemistry, 6.02 times 10 to the 23rd, and that is basically 6 trillion million, so a very, very large number, right? All right, another common thing that we're going to use for a lot of our calculations and numbers in general chemistry is the metric system, so hopefully you have some familiarity with that, but if we're reporting a mass, it should be in grams, distance will be in meters, liters is our volume. Then some more common ones maybe, second is something that you're probably very used to using. When we get into the amount of a substance, we can call that a mole. And current, which we probably won't end up using this semester, but still a good one to know, is an ampere or an amp. Okay? And those are the abbreviations given for them. Within the metric system, we also have prefixes. So this combines essentially a way to represent very large or very small numbers without having to use scientific notation. And so common ones for us, well, let me start in the middle here and say essentially between deci and kilo is our base unit, so that would be times 10 to the 0. But when we have positive numbers, we know they're bigger. So for example, kilo, so if you think about like a kilogram or a kilometer, that means 1,000 grams or 1,000 meters is represented in a kilometer or a kilometer or a kilogram. Mega, giga, tera are other larger abbreviations or prefixes, I should say. And so I often think of this with like computers. You have a megabyte or a gigabyte or a terabyte. Then in chemistry, we tend to use the smaller ones more. So deci and centi, we don't use a ton, but then these later ones we use quite a bit in chemistry. So milli is 1/1000th, micro is 1/1,000,000th, nano is 1/1,000,000,000th, and then pico is 1/quadrillionth, I guess you would say. And so we do frequently use these in chemistry. We're going to be using them more in class and then in later weeks. So good things to know. Okay. Switching gears a little bit, so getting back to atoms that we talked about in class on Wednesday, we're going to talk a little bit more about how we know that atoms exist and how we represent them. So there was a guy about 120 years ago or so that found that if you shot a particle beam at an extremely thin gold foil, you would actually get some of the particles that would bounce off of it. And about 1 in every 20,000 of them would bounce back. And what he was able to essentially show here is that there's something solid in the middle of our atom. And we know that now, of course, to be the nucleus. And he was also able to show because some of the particles went straight through, but some just kind of glanced off. And so some of them were actually attracted to the positive part of the nucleus and varied just a little bit. So you'll see some hit the nucleus and bounced off, some just kind of bent as they went close by a nucleus. Okay, so that is one example of a model of an atom that is a bit older. One that we're going to use more this semester is the Bohr model of the atom. So after Rutherford, there was a guy named Bohr who proposed a model of the atom where our electrons and protons are held together based on the attraction of charges. So a reminder, our protons are positive, our electrons are negative. And Bohr hypothesized that our electrons have a circular orbit around our nucleus. And that is why they don't just fly away all the time. Also within that, the closer the electron is to the nucleus, so this black dot being our nucleus, the closer it is, the harder it is for the electron to be removed. However, they can move between levels using light energy, basically. And so we have different radiation here. We're going to talk about this more next week, but essentially we can get between our different energy levels, our different orbits, by putting in or taking out light energy. Okay. So that's it for this pre-lecture. Hope it was useful, and I will see you in class soon.